Okay, I hope everyone is fortified after the tea break. We've got 3 talks now. Um, and I'm very happy to be at the point in my own lectures where I get to talk about feedback control systems. This is, you might remember me saying on Monday that I think physics really let itself down by letting engineers claim this material for their own. It is so beautiful, so charming. We ought to call it physics. And fortunately, we get to do a lot of feedback control systems in gravity wave interferometers. So I hope to uncover some of the beauty of it and the utility of it as well. Okay, lecture 8. So I want to look at this from first principles, ask the question, what is feedback and why might we want to apply it? Why do we want to apply it? And then look into, in a little bit of detail, how feedback works, how to understand what we're doing when we close a control loop around some system. What are we hoping to achieve? What are the limits to what we can achieve? What are the ways in which it can go bad? And sometimes it can go bad. You can see I've prepared the way by taking a standard diagram and put it up here so that I can refer to it as we look through some of the discussion of how feedback goes. All right, so there's a number of places in this field of physics and technology that we're spending this week together talking about where feedback makes all the difference. One classic case that, of course, we've been talking about off and on all along is how do we match, sorry, Ali, I didn't draw the laser. How do we match the wavelength of light from a laser to the length of a cavity so that the cavity is resonant and does its storage function of being a reference cavity or an arm or whatever it is. Something we need to do over and over and over at various spots in our interferometers. But here's maybe a less obvious place, but I think we've probably mentioned this too. We've got pendulums, and as we were talking about earlier, to make the thermal noise low, we try our hardest to make the resonance have a very high Q. That's miserable. A 1 hertz thing with a Q of 10 to the 8th swings for a really long time if you disturb it. So modifying the response of a system in a controlled way that lets us keep the good properties we want and tame the properties that are less advantageous is another application of feedback control. And Rana already showed us a fair amount about the use of feedback to give us vibration isolation. I'll say a little bit more about that here, just as part of the overview of what we're doing. So here's a slide that I copied on the board. This is a diagram intended to capture a generic description of a feedback control system, and it's worth walking through it carefully because I'll want to refer to various parts of it so that we can understand what's going on. And there's some terminology we need to use, and then there's there's many aspects that aren't terminological but are deep scientific interesting things as well. So perhaps the strangest terminology in the field is the term plant. And let me just say that the plant is the name that that control engineers give to the thing that's delivered to them and say, you fix it. And so usually, I mean, we're not quite in the situation, well, we're not really in the situation at all where we've got people who design an interferometer and then hand it over to control engineers and say, oh, you control it, right? Not that we actually understood the control problem from the beginning, but we intended to. So there wasn't a division of labor, but it's often the case in other aspects of the world that something is made, it needs to be controlled, but you can't really do anything to this except wrap around it the rest of the feedback control system. So let's imagine we've got something, and this may be an arm, it may be a whole interferometer, it may be some platform of masses and springs that we want to turn into a good low-frequency vibration isolation system. And every time I draw a box here, I'm thinking of something that has an input and an output. And also, these are things that are connected to each other in such a way that, unlike the stack of mechanical stages in a passive vibration isolation system, we can, in almost all cases, and I think in every case that I'll be discussing, treat things as if there's no back action from something downstream. A signal arrives, and the fact that I hook up a sensor here doesn't load the plant output. That's the generic belief. Okay, so here's a plant, here's its output. The plant output is an input to the sensor. If we're going to do control, we have to look at what the plant is doing, and based on what the plant is doing, figure out how to modify it. So every control system has a plant, needs a sensor. The output of the sensor, you could generically call the sensor output. It's almost always called the error signal in this trade. Sometimes we're looking at that in some way, or we care about what the plant output is in some way. We're almost always looking at the sensor output. That's the good way to actually, in many cases, see what the plant is doing. Okay, the output of the sensor goes to a block that I've called filter on this diagram. Usually I'll give it a longer term. I'll say compensation filter. That's where a huge proportion of servo engineering goes on. It's subtle enough that I don't want to say much more now, but I'll come back to it and talk about that subtlety in a bit. The output of the filter goes to a summing junction, and here's that minus sign that Ramanna can never see when people like me draw it. But there it is. I like to put an explicit minus sign. I drew it bigger over there to be sure that you could see it. Okay, it's a matter of taste whether you absorb it or make it explicit. I don't know, where I learned it, it was out there explicitly, so that's how I was brought up. So the output of the filter is an input to this component called the actuator, but it's often, not always, but usually, typically the case, that you have another use for this actuator anyway. The term actuator refers to some device that can act on the plant, serve as an input to the plant. Even if you didn't have feedback control, often you want to tell the plant to do something. So usually you have this anyway. So in a feedback system, make a summing junction, bring this in with a minus sign, this in with whatever sign you want, and make those two, the sum of those inputs be the net input to the actuator. The actuator's output is an input to the plant, and for things that one designs, that's probably about it. But one thing we definitely want to discuss, and it's extremely important in the applications in gravity wave detectors, is that in addition to the controlled input to the plant is often being kicked by the outside world in some way. And so we model, we say, okay, we've got two inputs to the plant, they get summed in some way, forming the net input to the plant. Okay, so it's hard to picture a servo mechanism, which is the other slang term for a feedback control system, where you can't identify something that plays the role of each of those functions. So the diagram will stay up there. Okay, so here I've just written on a slide what I just said, so we don't need to dwell on that. So now I want to talk about some applications of feedback. What sorts of things might you want to do where applying feedback is a good way to achieve that? And one of them, and it's one of the very important applications of feedback in our detectors, is to hold the plant near a chosen operating point. Hold the arm, a Fabry-Perot arm on resonance so it works. hold the whole Michelson with Fabry-Perot arms near the dark fringe. Lock the laser wavelength. Well, okay, let's leave those two as good examples. So this is a situation where, at least from most points of view, you might say there's no control input. You're not trying to do something interesting with the plant. You would just want the plant to sit there doing the right thing, and then you observe it. You record what a sensor says. Okay, so in this case, right, we get rid of, now I'll refer to this diagram. We imagine that we don't have this, but we surely have disturbance inputs. And the function that we're getting out of the control system is to reduce the sensitivity of the plant to disturbance inputs. To make it so that even though there's these disturbance inputs, we're in effect compensating for them by what the control loop is doing, so that the net input to the plant is small. So when we're talking about systems where feedback is doing this, the official thing that you see in textbooks is feedback reduces sensitivity to disturbance inputs. Okay, another generic kind of use of feedback is to modify the dynamics, such as making it possible to live with a pendulum suspension that has a high Q. Somehow make that work. And there, the function is just to say, all right, if I look at the poles and zeros of this thing, I just want to move them in the complex plane to some other place that makes more sense for me. So that's something that's often worth doing. Okay, so here's another version of this diagram, and one or two of you have already caught on to the fact that I tend to slip very freely, slipperily, and loosely between the Fourier domain and the Laplace domain. I apologize, but it usually works. Don't usually get into trouble. So this slide is a reminder that for most of the rest, or almost all of what the rest I'm going to do in this hour, I'm going to treat these objects as linear systems, which we hope they are, or when they're not, we hope by virtue of the feedback loop to have bootstrapped things into a situation where they are. And I'm going to use the frequency domain tools that we walked through yesterday for the analysis. Right before I'm done, I'm going to mention that there are ways to handle these without working in the frequency domain. But the frequency domain tools are so powerful and so beautiful, at least for one degree of freedom feedback systems, that I can't resist mainly concentrating on them. All right. Now, I'm going to make an assertion that in a little bit I will justify, but let me assert it first because it's really important. So we've got these four elements: the plant with its frequency response P, the sensor with its frequency response S, the filter with its frequency response F, and the actuator with its frequency response A. And now I'm going to take advantage of this wonderful property of working in the frequency domain to use the fact that if I want to know what the whole loop is capable of doing, the whole loop can be considered a block whose frequency response, if we were doing it in the time domain, we'd have to convolve the impulse response of this with the impulse response and so on. But instead, in the frequency domain, we just get to say the net effect of all these components that follow each other, cascaded one after another, is just the product of their individual frequency responses. And that's a mathematical fact, but there's a deeper fact of feedback systems, that this particular product, the product around the loop of all the frequency responses, which goes by the name, usually it's written G, unless you've already used that for something else. And in the books I was trained by, this thing is called the loop transfer function. Colloquially, in the lab bench, people would usually call it the loop gain. Okay. Anyway, this object is by far the most important thing you need to look at. Studying the values of g of f as a function of f tells you essentially everything you need to know about this servo, at least when it's properly operating in the linear regime, which is where these tools work. All right. Now, I want to assert the most important theorem that I'm going to apply. There's maybe one other that's almost as important, but this is basically it. This is a statement of the benefits of feedback, what feedback buys for you. And let's consider some frequency response or a transfer function from some input to some output. It could be one of these blocks that we've drawn, could be the plant, or it could be a pair of them that are neighboring, or whatever. Just pick a point in this loop as an input, pick a point in the output, and say, okay, call that frequency response H. And if you know the frequency response H without feedback, and the jargon is the loop is not closed. Say, for example, we just break that wire. Okay, that is. The jargon is that loop is now open, and now maybe I have a switch that I'm going to close. When I close the loop, that same transfer function that was h of f becomes the object h closed loop of f, which is equal to h of f over 1 plus g. And I have the plus because I made an explicit minus there in the diagram. Okay, so let's remember this and think about and walk through a bit what that means in various cases. First, though, I want to actually derive that statement. So let's do it. And I realized I needed to add a few other things to this diagram. So let's do it. We're going to call the signal that is the net input to the plant I. Call the plant output lowercase p. Call, let's see, what else do I need? I think I just need the actuator output A. Looks like that's all the labels I'm going to need. So by paying attention to those signals, I'm going to derive this theorem. Okay, so here is the derivation. Oh, I did need to label one other thing. D, the disturbance input. Okay, so the net input to the plant is the sum of the disturbance input and the actuator output. Okay, so far so good. Now, here's where it gets cool. A is in turn equal to the plant input times capital P times capital S times capital F times capital A with this explicit minus sign kept explicit. So it's A is minus I P S F A, which is to say it is minus I G. G being the loop transfer function. Now all I have to do is go up to that first line and plug in for A minus IG, collect my terms, and then I find that my net input to my plant was the original unclosed loop input divided by 1 plus G. Okay? And maybe I didn't want that particular statement. Maybe I wanted to know what was the plant output, closed loop case versus open loop case. So I just multiply that previous line by capital P, and I find that my closed loop plant behavior, it's the closed loop plant frequency response is just the open loop response divided by 1 plus G, And I could have picked any other block or combinations of blocks, and it would have said the same thing. So, everything is simple, right? If we want to manipulate the behavior of our system, just make a G that's much bigger than 1 with the proper shape so that it modifies that original frequency response to make a new net frequency response of whatever you want. Right? So this is so powerful it can do anything, right? I wish. And it's the difference between that wish and what can actually be accomplished that's one of the interesting, beautiful, or tragic aspects of control systems depending on what day of the week it is, depending on where you are in the design process. So let's first say a relatively obvious thing. So our modification of our original frequency response comes by having a factor of 1 plus g in the denominator. So a feedback control system does a lot where 1 plus g is big. It does a little where 1 plus g is of order unity. And it does almost nothing where g is much less than 1. Okay? So that denominator makes things happen. So tracking the loop gain, or 1 plus the loop gain, is the thing to do. So let me talk about perhaps the easiest to understand servo design problem that we have in the gravity wave business, and that's taming the Q of a pendulum. And I'm going to show how you design a feedback system that applies artificial damping to this to reduce the Q. So here's my plant, pendulum. I have a position sensor. I have a force actuator. And then I have a filter. So plant, sensor, actuator, filter, those are the 4 blocks. Now, what should I do in order to apply artificial damping? Any suggestions? What makes artificial damping? Or what makes damping? Rubber. Oh! Okay. Wrong. No, okay, we could do it, but what's something a little bit more generic to say than applying rubber? What do you want that mass swinging from a pendulum wire to feel? Yeah, some sort of drag, some friction, a force proportional to velocity, perhaps. Okay? So one thing we could do is take the output of our position sensor and take the derivative of it by some electronic circuit, and then multiply it by some value of an overall constant gain factor, which we want to have the freedom to adjust to get the right output. And then, with the appropriate sign, apply a force to this mass that is proportional to the velocity. Make sense? All right. Here is a Bode plot of the loop transfer function of the system we just described. So there's the resonance. Before I took the time derivative to get a velocity signal, I had something that was constant here, had a resonance, and fell like 1 over frequency squared. But what I'm showing here is that plant transfer function multiplied by I omega, which in the frequency domain is what a derivative is. So this was constant, now it's growing like frequency. This was 1 over frequency squared, now it's only falling like 1 power of frequency. And because I've paid attention to both real and imaginary parts of this transfer function, I can also plot the phase. And it's plus 90 degrees below the resonance. And then at the resonance, there's 180-degree phase shift in the negative direction. And then the phase is minus 90 degrees on up. Now, I haven't included stuff that you and I know also would go in the physics of a real thing, like the fact that there are other mechanical resonances in the system that I didn't describe, or that derivative circuits, you can't extend them to arbitrarily high frequencies. These are all important, but just to get the basic idea, let's put those aside for the moment. So that's going to be my G. It's got the plant response, it's got that filter response, and I'm assuming that the sensor is got a flat frequency response, and the actuator does too. Again, those things are not always going to be perfectly true, but they're good enough for this purpose. And now I want to illustrate here the open loop and closed loop response of the system for a particular choice of the overall multiplicative constant around the loop. So here in dashed line on this log-log plot, the dashed line is the original plant transfer function. And you see that high Q peak that we don't like. And now what I've done, let me show you how I chose, how I chose the overall multiplicative constant to achieve what I want. So I was careful to walk us through the structure of this loop transfer function, but what's the right overall gain level to achieve our goal? Do we want to be doing stuff well below the resonance or well above the resonance? No, we're just trying to tame that Q. So we probably want to set the overall level so that those of you who are close enough can see that I set this up so that 0 dB, i.e. 1 unity, is right there. Okay? So the place where G is much larger than 1 is in a pretty narrow region right there at the resonance. And G is, call it much less than 1 or somewhat less than 1 over here and over here. So with that particular choice of overall multiplicative level and closing the loop, here is the result. Here in the narrow region of the peak, where G was much greater than 1, we've made a big difference. And by appropriate choice of signs/phases, we've just made 1 plus G a big thing, pulled this down. We now have a little bump instead of a big bump. But there's almost no changes to the response there. So designing a servo is easy, right? Okay. I'm not going to walk through this example in any detail at all, other than to say that if you somehow bootstrap a Fabry-Perot cavity into being locked, into there being a lock between the wavelength, a resonant match between the wavelength and the length of the cavity, then in the vicinity of that operating point, you have a linear system where a signal seen at the output of this mixer in a Pound-Drever Hall readout system gives a linear measure of the length of this cavity. And so with the appropriate choice of sign, you can feed it back to one of the mirrors to keep things in lock. Or you could feed it back to the laser to move the wavelength around, or a variety of things. I don't want to walk through this because the real thing, you'd want to think in detail about the dynamics of where you're applying the control. And we do this all the time, but I don't know how edifying it would be to walk through a particular model example right now. I do want to say a tiny bit more about this example. This is a conceptual diagram of a rather crude sort, but enough to make the principle clear, of active vibration isolation. So what I've drawn here is something that's sitting on the ground, and then there's a platform suspended resonantly from it, and a second platform here, resonantly suspended from the first, that I'm going to play two separate roles just for simplicity of discussion. I'm going to say that because this platform has mass and it's on a spring, the relative displacement of this mass with respect to this mass functions as a vertical accelerometer. Now, when we actually do this in real life, we put separately engineered accelerometers on rigid platforms for a variety of good reasons. But just for thinking about this in a 1 degree of freedom sense, just the vertical, give me this simplification. So the idea, or you could let me say, oh, I've just drawn a vertical seismometer, vertical accelerometer with a really big mass. Either way, it doesn't matter. So I've got a position sensor drawn here that is measuring the separation between these two masses. And it's measuring that because, let's say, this platform was in the process of being accelerated upward. We would see these springs compressed, and we would know that it was being accelerated upwards by the disturbance input coming this way. So we use this separation as our error signal, or our measure of it through whatever position sensor we have as our error signal. And appropriately filtered, we feed that back with appropriate sign again to apply a force to this platform to counteract whatever force has originated in the environment and made it through these springs. Now, this is a little more complicated a system of resonant masses than the ones I talked about yesterday, but actually writing down the coupled equations of motion for a simple harmonic oscillator on top of a simple harmonic oscillator is not very difficult, and including a forcing term that is proportional to some version of the separation between the top mass and the middle mass is not too hard. I just want to sketch for you what the loop transfer function looks like. There are two modes in this system, two masses on two springs. And the loop transfer function that I've diagrammed there ends up showing those two resonances and having a proportional to frequency squared characteristic below the two resonances, not changing very much in between and falling like 1 over frequency squared above the second resonance. And now here is the phase part of the Bode diagram of G. Should use a different color, shouldn't I? All right. One can learn a lot from considering this transfer function. That's why I want to dwell a little bit. So let's ask what happens if we assign some overall multiplicative constant to the loop transfer function so that this is 0 dB, the unity gain level, and close the loop. An amazing thing happens to the closed loop transfer function. And I think I'm going to get rid of this diagram now. So if we ask how a disturbance input, shaking of the ground, moves that top platform without feedback, it looks like this. 1 over frequency to the 4th, because there's 2 resonant stages, 2 resonant modes. And when we close the loop, we make it as if there is a much lower frequency resonance in the system, which lives at this frequency, the lower unity gain frequency in the jargon. And then this resonance kind of disappears and reappears up here, and then outside the range where G is greater than 1, the response is the same as the original response. That's basically how active vibration isolation works. Now, in a moment, let's come back to this when we talk about stability, because there's something that's very twitchy about this loop transfer function, namely that the phase of the loop transfer function goes to the wrong sign, both at low frequencies and at high frequencies. This can work. It does work. But you have to do something a little bit more to make it be well behaved and not just on the verge of being unstable because of those sign changes. I'll say a little more about that in a bit. Okay, so in the engineering literature about feedback, there's this very learned discussion about benefits of feedback. I've been walking us all through that, and so-called costs of feedback. And costs of feedback can include the fact that you need some extra components and that you need to engineer them, but that's not really the most important cost of feedback. The most important cost is that with feedback, you can take a system that maybe didn't have every property that you want, but at least was going to sit there when you didn't do anything to it, and turn it into something that all on its own can go crazy. Can start howling at some high frequency, or can slam in one direction until it hits some motion limit, can go unstable. So ensuring that the servo not only is designed to do what you want, but to actually do it instead of going unstable is the thing that takes the most agony, the most engineering effort, and the place where you have to be the most careful. And now we come to what I want to say about the filter F. That's the place where you try as hard as you can to achieve your performance goal. Try to make G big every place where you would like to modify the original frequency response of the system, the open loop response. But it's also the place where, if you're not careful, you can actually introduce problems that will cause the system to go unstable. And therefore, it is the battlefield where you have to step back from your overambition and modify things so that the properties are okay. And I have various ways of saying this. This is the polite way. This is a very rich subject. Another way of saying it, this is where you will tear your hair out. This is where you will try over and over again to accomplish the impossible until reality convinces you of what can be done. So we know that we have to think about the possibility of instability, because it's easily possible to make G be minus 1. And so formally, that denominator diverges. And here is a case where, to a very good approximation, we have in fact naturally stumbled into a situation where a good part of our frequency range has G equals minus 1. Now, the first time I designed a servo, I said, well, okay, let's just not let G ever be minus 1. Let's just make it big, and then we're done. But the laws of nature do not allow us to have G be a large thing, have a large value everywhere. At a minimum, there must be some high frequency at which you just can't push, okay? Causality says, okay, there's speed limits. Now, this is not usually where we stumble, but just as something to remind you that you can't possibly be as ambitious as I first was. Just to get signals around at high frequencies and make things capable of moving is not allowed at arbitrarily high frequencies. In fact, I'll mention in a little bit what's a much more important limit than this, but we're not able to do the naive thing. Now, here are some words to remind you of what the real limit actually is. When I make this active vibration isolation system, my actual loop transfer function is more complicated than this. And the most important problem that happens is that in my mechanical connection somewhere, when I'm trying to push, suddenly I encounter a resonance that I didn't model. Some part of the actuator is resonating and can grow another resonant peak. And at that same spot, I should carry around all of these. Where I was just barely skirting minus 180, boom, I can have another minus 180 from that resonance. And when that happens, almost always, the system goes unstable. And this is the form of instability where it starts to scream at this frequency. And this is generic. If you're trying to make mechanical servos all the time, you're running into to actuator limits like this, to unmodeled resonances. So, what are we to do? We have to restrict our ambition and ensure that we're not trying to do feedback with the wrong sign at this spot. So, what turns out to be a generic rule of thumb for almost all servos is not make G a large number everywhere, but instead make it large at low frequencies and then roll off the magnitude of the gain before you encounter one of these resonances. So loop transfer functions generally are declining functions of frequency. But now, here's another problem. Let's say, okay, I've learned that lesson. I'm going to roll my G off steeply so I can have good performance at low frequencies and avoid this problem of resonances at higher frequencies. There's a theorem that I think I wrote, in the next slide. Let's just skip to it. There's a theorem of complex analysis that says if I have a system that is causal, where we live in the world, that there is a limit to one's ability to specify an arbitrary frequency response for a causal system. And in particular, the limit comes in a way that at least is often as simple as this statement here. If I decide I want the magnitude of G to be rolling off like some power of F, and I do that over a broad enough band, then I know what the phase associated with that is going to be. It's going to be 90 degrees, negative 90 degrees times the number of powers of frequency that I want to roll things off at. And to not run at least into naive problems with signs, it looks like I can only roll this off at most at 2 powers of frequency. Now, I have built, Rana has built, perhaps Ali has built loop transfer functions that evade this, but it takes some real care because you can't really evade it entirely. You just need to say, I'll make it steep for a while, and then before I hit unity gain, I'll shallow it out, bring my phase into the right orientation, and then I'm okay. But you want to make G really steep. There's some real limits to it. You can't make G as big as you want, only as big as is allowed here. Every idea you start out when you're a beginning servo engineer was wrong, and there's only a few things that you actually are allowed to try. Okay, Rana wanted me to be sure to say this. This is something I probably would have remembered to say in any case, but you've caught me doing something which we all do when we design servos. I caught Ali doing it too, because we all do it, and that is talking about stability looking at the Bodhi plot of G of F. And here's sort of one more thing where life is more complicated than you would like. Usually I guess right about stability when looking at the Bodhi plot, but there is no single rule you can write down that says if a Bodhi plot of a loop transfer function obeys these rules, the servo is stable. If you want to check the stability of a servo loop, you have to use other tools. I'll mention one or two in just a moment. But in particular, the rule that we always are tempted to use, but it doesn't always work, is to say, okay, as long as I'm within plus or minus 180 degrees of the naive sign for all frequencies where G is above 1, then I'll be stable. That works most of the time. But if that's all you do, you may have a nasty surprise for yourself when you close the loop and turn it on. The stability test that I like, and this one always works if you remember to apply it and apply it carefully, is instead of plotting a Bodhi plot of G of F, make yourself a complex plane. And then, with frequency as a parameter, plot G of F as a complex function of frequency. So that's the plot you're invited to do. That plot is called the Nyquist plot. And then the stability test is to ask whether in the complex plane this complete locus of G at all values of frequency, does it or does it not encircle the point at minus 1, 0? If it encircles it, don't build that servo. It will be unstable. If it doesn't encircle it, you're okay. And occasionally, you design things like that original version of what I showed that in principle is just barely stable for arbitrary values of overall gain. The naive version of that servo just barely kisses this axis. But what it actually does when you actually build it with real things is it crosses the axis. And as a result, you'd better not turn the gain. Turning up the gain then means blowing this up. Better not let that crossing of the negative real axis appear at the left-hand side of 1. So that's something that, that's a tool that servo engineers who still like the frequency domain, as I do, can apply. You can also, if you like, and I've applied this one myself, take the closed loop frequency response and just calculate the values of all the roots, and just ask, okay, I've got this model frequency response. Do all all my my poles, my roots of my closed loop response system, that they all lie in the left half plane. If so, I'm okay. If not, better not build it that way. And this method is called the root locus method because usually it's applied by calculating those roots for one value of overall multiplicative gain, then another, and see how big the overall gain can be before you have roots that cross into the right half plane. Now, the last thing I want to say is that I have bared my soul. I love frequency domain analysis, but sometimes servos are just too complicated. And when they get too complicated, most seasoned engineers say, I'd better just study the dynamics by studying the equations of motion of the system. There's a huge literature that I'm not able to summarize for you all in any enlightening way, called state space control, which is a formalized, routinized way of writing equations of motion in a certain way and applying a variety of tools. So if I've tempted you and you're getting into this, study that on your own. But I hope I have convinced you that this is a cool subject with some charms, with some tears, but eminently important for what we've done. Let me just close with a couple of diagrams I stole from a talk of Rana's years ago. I hope you remember this. That we've thought over and over about an interferometer as an optical system, but it is also the plant of a rather complicated feedback system where there are many degrees of freedom that you want to hold at operating points. There are many bits of dynamics that you want to control, and there are surely many disturbance inputs that you want to minimize. And so, in addition to everything else, the gravity wave business is a really exciting and challenging control system problem. So I'll stop here. Okay. Questions before I relinquish the stage? Not? I will relinquish the stage.